All right, the next topic in chapter 3 deals with Rolle's theorem. Now, Rolle is an interesting character. He's a French mathematician, one of the biggies in Europe in the 1700s, who just didn't buy into infinitesimal calculus as Leibniz and Newton both had espoused upon. But he did develop this interesting little theorem here, and this is a theorem that is used a lot in calculus, even though he didn't agree with it until much later on in his life. And he goes, okay, I was wrong. It's cool. So here's this theorem. Let f, your function, be continuous on the closed interval a, b. So it starts at a and closes with b. And differentiable on the open interval a and b. So in other words, it's continuous, can't be choppy, can't have the different areas coming from the negative positive side. So it has to be continuous, and you got to be differentiable, which means you can't have 0 for a denominator. If the function of a equals the function of b, so the two endpoints of your interval, if the function of them, if both functions are equal to each other, then there's at least one number c on that interval AB such that f prime of c, or the derivative of c, or the slope of c, or at c, or just plain slope equals 0. So we got to have the horizontal slope at that point. Okay, so your problems are going to be dealing with this very idea. So we're going to take a look at some of the problems on page 176, and we're going to show all these little details that he's talking about here. We'll start with number 11 on page 176. And the problem says that the function of x is x squared minus 2x, and the interval that we're looking at here is 0 and 2. So the first thing we have to do is make sure that the function of 0 and the function of 2 are the same thing. Doesn't make any difference what number it is as long as they both come up with the same value. So the function of 0 is 0 squared minus 2 times 0, that is 0. And then the function of 2 equals 2 squared minus 2 times 2, 4 minus 4 is 0. So that's true, that works out. So that little statement that he made here, where f sub a equals f sub b must occur, then there has to be at least one number c such that the derivative of c is equal to 0. C being a point somewhere between a and b. Okay, so let's take a look at that. So now we need to find the derivative of x. And so when we do that, we get 2x minus 2. Now we set that equal to 0 and solve for x. And this is going to give us 2x equals 2, and x equals 1. And then this is between 0 and 2. This is our c, and there's our answer. Okay? Now the reason why we knew this, the reason we knew that this was continuous is because if you look at the graph for that, you would see that it's indeed a continuous curve. And we knew that this is differentiable. This has had no denominator and no weird absolute value thing going on or anything. It's straight up normal equation. So this will be true for Rolle's theorem. Number 13. Given f of x equals x minus 1 times x minus 2 times x minus 3, and the interval here is 1 and 3. Okay, again, no denominator, so I'm not really concerned about not being differential. If you were to graph this out, you can see that this is a curve with a third-degree curve. So if you have to look at f sub 1, well, you know that it's going to get 1 right here. 1 minus 1 is 0, so this is 0. And f of 3 here, we put the 3 in there, and 3 minus 3 is 0. So these two are indeed equal to each other. So this fits all 3 requirements for Rolle's theorem to work. So now we need to find a C that fits this between 1 and 3. So that means we have to find the derivative of this. Now, what I'm going to do at this point, I'm just going to go ahead and multiply all these out. X minus 1, x minus 2, take that answer and multiply by x minus 3. I'm not going to bore the details, you can go through, but I will tell you that fx turns out to be 3x squared minus 12x plus 11. Okay, you're not sure how I got that from, oh, well wait a minute, that can't be 3x squared. That's just the silliest one. Oh, yeah, that's not right. Oh, that's the derivative, I'm sorry. That's the derivative. Okay, let me go back to the f of x. I looked at the top wrong number now. When I went through all that, I got x cubed minus 6x squared plus 11x minus 6. That's what I got when I multiplied all these together right here. And then I took the derivative of that to get this value right here. You can see where that came from. Sorry about that. Now what I'm going to do is I'm going to set that equal to 0 and solve for x. Well, this is not factorable. So this could be an issue here. So we're going to have to plot form that. Now, if you don't have a quadratic formula in your calculator, you can get it ASAP. But I plot form that thing, and I get 2 values for x, and they were 2.58 and 1.42, both of which fall between 1 and 3. So in this particular case, we have 2 C's that fit this requirement. So these are both equal to the C. Okay? Number 15. Again, it's on page 176. This is f of x is equal to x to the 2/3 power minus 1. And the integral for this is -8 on one side and 8 on the other side. Okay? So, now I need to make sure that this is going to work. So, take the function of -8, and that's going to be -8 to the 2/3 power. Well, the cube root of -8 is -2. And -2 squared is positive 4. So do the same thing with positive 8. It was 8 to the 2/3 power. And the same thing, cube root of 8 is 2 to the 2nd power 4. So these two are equal, so that's looking promising. So now I'm going to do the derivative. Well, again, you do a graph of that. I think you find that it is continuous. Well, maybe not. You may not. Well, yes, you will, I guess. But here's the situation. You find f sub prime of x. 2/3 is brought in front, so that's 2/3 x. Subtract 3/3 gives you -1/3. And then this drops out, and so this is what you get. Well, if you rewrite this, and then you see what the issue is here, this becomes 2 over 3 times the cube root of x. This is not going to be continuous because x here cannot be equal to 0. And since that is the case, this does not follow Rolle's theorem.